9.3 Taylor Theorem. Take a minute to read the essential questions for this lesson. Now that we know how to find a Taylor polynomial for functions, and especially sine of x, let's talk about how accurate are we. We want to find a good substitute for sine of x in the interval from negative pi to pi. How many terms do we need in order to be able to meet that accuracy? Now, what is accuracy? Well, it's going to be the difference between the Taylor polynomial and the function, and we're going to be set some kind of tolerance. How close do we want these to be? Now let's take a look at the Taylor polynomial up to degree 13. Now that Taylor polynomial has this as its value right here. And when we take the difference between the value of the function and the Taylor polynomial approximation, this one, when we map this out, we're going to find this represents the error. Now remember, this is an absolute value sign, so that's why all of these values are going to be absolute. Take a look especially at the fact that close to 0, that there's no error, but as you farther and farther you get out into the ends of the interval, that's where the most error. So the most error is going to occur right here toward the end of the interval. All right, now truncation error is you're going to go out so far in the polynomial, and once you go out to that point in the polynomial, the rest of it we just drop off. We just truncate or eliminate. And everything we drop off is error. That's how far off we are. Let's take a look at truncation error in a geometric series. Here is the geometric series that's approximating this function in the interval from -1 to 1. And what we'd like to take a look at is all the other terms that we eliminated, which are right here. These are all the terms that we are no longer considering once we use a Taylor polynomial. Now this happens to be a geometric series. The ratio is x squared, so we can take the rest of the series that we have eliminated and actually write its error. And this is it. Here's the error. Let's go ahead and graph it, and again it looks very similar to what we saw before. At the ends of the interval is where the most error occurs. In close, those values close to the center are going to be the most accurate. Now what happens when the series is non-geometric? And that's where Taylor's theorem comes in. All right, one more look at the geometric series. These are for different powers, 2, 4, 6, and 8 when we're taking a look at the truncation error. And the farther you go, the more terms you take in the Taylor polynomial, the truncation error becomes less and less. So the truncation error, you can see, is a lot less than if you stopped at n equal to 2 or 4 or those others. Okay, here's the Taylor's remainder theorem. Your task is to understand the theorem. We're not going to prove it. That's for higher level courses. Okay, so here is the polynomial, and the rest of the polynomial is what we call the remainder. And that remainder, or that truncation error, can be written in this form. It's actually the very next term, so it's the very next power, n plus 1, evaluated c, we're going to talk about what c is, divided by the factorial, and then the polynomial to the n plus 1 power. So this right here represents all the rest of the terms that we have eliminated. All right, and this remainder is a way to describe convergence for the series. So if the remainder goes to 0, as n goes to 0, we say the Taylor series generated by the function f converges to f. So here's a way to say, yes, this series does match the function. All right, and here it is again. It's here's the remainder theorem, and it's the difference between the function and the Taylor polynomial, and it can be written as this. And again, we need to discuss what's the c, and this c is a value between the center and the x in the interval that you're talking about. Now, we're now ready to talk about that c. Actually, that c is some value that will force that derivative to be an upper bound. In other words, it's going to be, this is going to represent the maximum value of that derivative in the interval. And a lot of times we just write it this way, m for maximum. It's the maximum value. Okay, let's go ahead and do a problem where we can see this maximum value. So we have a Taylor polynomial of degree 5, and we want to see how far off we are going to be when we say sine of 1/2. So our center is 0, and our x value that we're looking at is 1/2. A is equal to 0, and x is equal to 1/2. So we have this Taylor polynomial to the 5th degree, and then we have the remainder, and it's remainder sub 5 because we took it to the 5th degree. The remainder is that same number. Now we want the upper bound, and that remainder sub 5 is really the very next derivative evaluated at some c in the interval between 0 and 1/2, and we'll have that 6 factorial, and this is going to be x to the 6th power, and our x happens to be 1/2 right here. X is 1/2. Now we can decide right now for an upper bound, especially with sine. Remember that sine, its largest value is 1. And so what we can do is our maximum value here, we can just put as 1. And so we're going to have 6 factorial, this denominator, and we have 1/2 to the 6th power, which is 2 to the 6th power. And this simplifies to this. And when we put it into a decimal, we have this. So this tells us that when we use a 5th degree Taylor polynomial for the sine of x, this is how far off we're going to be. And that's pretty good accuracy. 1, 2, 3, 4. It's not till the 5th decimal place that error starts. All right, let's take a look at e to the x. And we're going to take a degree 4. So it means our remainder sub 4 will be the very next derivative to the 5th power evaluated at some c. Remember that a is equal to z because that's the center, and we're trying to evaluate at x equal to 0.2. So our c is somewhere between 0 and 0.2. And we're going to evaluate our x is 0.2, and the largest this can be, remember going from 0 to 0.2, the largest that e to the x can be is e to the 0.2. And we have 5 factorial, 0.2 to the 5th, and this is our accuracy right here. And remainder is always going to be absolute. Okay, another way that we use the Taylor theorem is to take a look at how many terms do we need when we're set an accuracy level. Say we're set, you have to be within 1/1000th. And so again, we don't know the degree that we have to use, so we have to use n. So this will be sine of n to the 1 all over n plus 1 factorial. And we know that sine goes between -1 and 1. So we know that this value right here, the maximum will be 1. So that's why they write 1 over n plus 1 factorial. So this is the term here that we want to be less than 0.001. So at this point, we just make some guesses. Start at 5 and see if that works. Now remember, this is sine and we aren't going to get any even powers. So after you try 5, go ahead and go to 7. And it says here that t sub 5 and t sub 6 are the same Taylor polynomial because t sub 6, remember, has not that added term. Remember that the sine at that point is 0 and we don't get that term. And so it's just kind of a guess and check method until you find the one that works.